During the inspection of the reactor, a foreign object was found blocking parts of the lower plenum, starving coolant to some of the fuel elements.
That right there is the origin of the FME program. Today we're going to be looking at another one of Plainly Difficult's videos, specifically a brief history of the Fermi 1 meltdown. This accident did a similar type of damage to the 3 Mile Island event, but for whatever reason didn't inspire the same level of fear in nuclear. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's check this one out.
Liquid sodium reactors have a sordid history, as many have experienced some kind of incident. A partial meltdown in Michigan would fuel the fire for the anti-nuclear movement. However, unlike many nuclear events, the dangers to the public were negligible.
So it's a sodium-cooled fast reactor. So it uses liquid sodium instead of water as its primary coolant. And the sodium is also the moderator, which means the thing that slows down neutrons produced from fissions so they can cause more fissions more effectively. And it's a weaker moderator than water, which enables the neutrons to retain a lot of their speed, hence the term fast neutrons. So one of the main advantages of that is you can use a uranium-plutonium mix, at least back then. Could also use thorium and less enriched uranium. This not only means you're going to get a greater fuel utilization out of it, meaning you're going to have less fuel left over that needs to stay in spent fuel pools, but it also means there's going to be less of those nasty fission products that you're going to have to manage, which are a bigger hazard, at least as far as dose to the public, than things like uranium, plutonium, or thorium. So the overall radioactive dose risk is going to be less. Other advantages are sodium has a high boiling point. So for a given pressure, you can run the reactor at a much higher temperature without the risk of boiling. Because what happens when you boil away your coolant and the core becomes uncovered, that's what leads to fuel damage and fuel melting. And running your reactor at a higher temperature, that's just going to make your thermodynamic cycle more efficient. Because this is just an old school Carnot heat engine, which means if you make the hot thing hotter, or the cold thing colder, so that is to say making your cooling water for the condenser in the non-nuclear plant colder, that also makes it more efficient, which is why nuclear power plants are actually more efficient in the wintertime. Sodium's also way better at heat transfer. You don't need it to be highly pressurized because sodium is going to maintain itself as a liquid at a lower pressure without boiling. You don't need the super high pressure vessels that you would for a pressurized water reactor. However, the biggest hazard associated with it is sodium is extremely volatile. You really don't want this thing to leak. It reacts explosively with water, and at high temperatures, it ignites when exposed to oxygen. So, fire risk and fire that cannot be fought with water. Mainly use things like powders or suffocated with nitrogen. And the sodium can become radioactive by virtue of neutron capture when exposed to the neutron field from the reactor. It has a short half-life of about 15 hours. So it's not the same level of hazard that, say, nuclear waste does. But it does get used, so you're also going to need the facility in relatively close proximity to, so you need to manufacture liquid sodium, typically right next to one of these things. So a lot more chemical hazards.
This is the second video in a row that involves a partial fuel meltdown, and has a fascinating footnote for a reactor design that never really took off in mainstream commercial power generation. Today we are looking at the 1966 Fermi 1 fast breeder reactor meltdown. This isn't the first time I've covered an incident involving a sodium-cooled fast reactor, but it probably won't be the last. I'm looking at you, EBR1. The Enrico Fermi nuclear power plant is a generating station in New
EBR1 involved a loss of coolant flow to the reactor, partially due to poorly designed fuel elements, and partially due to the operators not having the tools they need to detect the problem. In
Berlin Charter Township, Monroe County, Michigan, which is about here on a map. The site is named after Nobel laureate Enrico Fermi. and began construction on an experimental reactor in 1956. The site would get a second reactor with construction beginning in 1972 and being commissioned in 1988. Fermi 2 was a boiling water type reactor, and a third identical reactor was planned but cancelled in 1974.
Fermi 2 still operates today. Same cannot be said about Fermi 1 though.
Into the commercial use of a fast breeder reactor has led many organisations down the path of building an experimental unit, and Fermi 1 was no different. The allure of a fast breeder reactor is that the use of liquid metals such as sodium does not act as a moderator like water does. The reactor type uses
It's a weaker moderator. It technically still moderates, but I get what he's saying. It doesn't slow it's not going to slow the neutrons all the way down to the thermal spectrum. It just slows them down a little bit, so they can cause fast fissions. So technically, if it didn't moderate at all, it wouldn't cause any fission.
Rich fuel and can sustain a chain reaction with fast neutrons. This type of reactor can create more fuel than it consumes, meaning it could in theory solve fuel shortage issues. This is done by using a fertile blanket of non-fissile material, such as depleted uranium. However, these types of reactors have two main disadvantages. Firstly is cost, rendering the type not ideal for commercial applications, and the second is the type of coolant, liquid metal, which can become volatile when exposed to the moisture in air.
I'm glad he brought up the cost, because that's one thing that does hold it back, and it's kind of also related to all the care that you need to handle the hazardous liquid metals, and also just manufacturing this stuff. But especially as we're looking further away, if you was to extrapolate that to now, why don't we see a lot of these things now, is a lot of this technology is getting lost, and a lot of people just don't know how to build or operate these things. You could say that's true about any nuclear power plant, but considering these experimental reactors are getting older and older, that does contribute more to the cost. I'm really glad he brought that up. And I would argue these two are related.
The event of a coolant leak could be deadly. Now that is a really, really rough and brief overview of fast breeder reactors. Let's look at the Fermi one in particular. The reactor received its sodium coolant in 1960 and achieved criticality in 1963. The reactor was tested at low power in its first couple of years of operation. Power testing above 1 megawatt commenced in December 1965, immediately after the receipt of its high power operating license.
So when he says low power testing, that's well below 1 megawatt, even in the watt range, like tiny fractions of a percent of reactor power. And some of this testing, it's known as low power physics testing, is done between every fuel cycle, and it's done in a lot more in depth when you're getting a brand new reactor, which is why there's such a big gap between first criticality and commercial operations, usually on the order of several months. It's even one thing that's done after each individual refueling outage, because a core design, you're given a nuclear design report. At the plant that I worked at, it was done and verified by both reactor engineers in-house as well as Westinghouse's own reactor engineers, with estimates, the fuel enrichment, the fuel layout, which looks something like a Scrabble board, because the enrichment is not exactly the same in each part of the core, and you're going to need to look at how much power. And the reason for that is because you want a uniform distribution of fuel throughout its entire cycle, and that changes a bit over time as the reactor produces power. Now, I suppose theoretically you could make one uniform in a perfectly spherical reactor with an omnidirectional perfect source dead center, but that's way too expensive and impractical to design something like that. On-site and fuel vendors like Westinghouse, their reactor engineering teams play a game of Scrabble. And then they get into the control room and validate their game of Scrabble. Make sure all the tests look normal and corresponding with all the calculations and models that they run before you finish starting up the reactor. And this can all be done very safely at very low power. It's low because it's really safe. You can intervene long before having any risk to your operating margin. And it's also low because it's inexpensive. You're not burning all of your nuclear fuel during your testing when it's not producing electricity.
The reactor had 2 cooling loops, both using liquid sodium. The first loop passed through the reactor core and went through a heat exchanger, secondary loop flowing through it. The heat transferred into the secondary loop and then went through a steam generator for use with a turbine for electrical power generation.
So it's interesting because we're still using good old steam. There's just an extra loop in the middle because you have your primary sodium that cools the reactor, then you have your secondary sodium is the shell side of your heat exchanger in the middle, but the tube side for your steam generator. Now, one advantage of this is there's an extra layer of looping, an extra layer of tubes to prevent radioisotopes from hitting the secondary part of the plant, compared to, say, a pressurized water reactor, which just has one. Though this adds to the cost, throwing in an additional heavy-duty heat exchanger that's designed to handle liquid metals.
Flowed upward from a high-pressure plenum connected to the discharge lines of 3 primary sodium pumps. The sodium flows upward through the individual core and blanket subassemblies into the large upper plenum, then flows by gravity to the intermediate heat exchangers and then to the suction side of the primary pumps. The plant was designed with a 430 megawatt capacity, however the maximum reactor power with its first core loading, core A, was 200 megawatts.
So you can tell this is still kind of an experimental design because most reactors are way, way higher than this. The plant I worked at, which is one of the larger ones, had over 3,800 megawatts in the reactor. That's not to say you can't make something that big with a liquid sodium reactor, just this particular one, this is early stages of that technology.
The reactor was capable of creating 69 megawatts of electrical power. The reactor...
That checks out. It's about a third a typical steam cycle. Though this one, you would think you could do a little bit better just because you're running at a higher temperature, but you're ultimately limited by water and the pressure and the heat and pressure in your steam generator.
Contained in a stainless steel vessel, sealed at the top by a rotating shield plug. The core was surrounded by a blanket of depleted uranium. The total diameter of both core and blanket was 80 inches and had a height of 70 inches. The core of the...
It's a much smaller reactor than the one I was used to. A lot of nuclear power plants in the U.S. are about 10 to 12 feet long. That's how long the fuel assemblies are. And the plant that I worked at was 14 feet.
It consisted of a cylinder of 31 inches across with a depth of 31 inches. This was made up of the control rods, neutron source and multiple fuel sub-assemblies, of which were 2.6 inches square by 8 feet tall.
You can see here is their Scrabble board. And that's another reason why it's not completely uniform, is the control rods have to go in there, the sources have to go in there, and again, unless you can have your magical, circular spherical shells, I guess, of control rods, then it's not going to be perfectly uniform. It's still not perfectly uniform, but it's close enough, and it's continually monitored, and you have to move the control rods over core life, so it helps maintain that uniformity.
Subassembly had 140 pins of 25.6 enriched U-235, resulting in a total mass of 4.75 kilograms of uranium-235 per subassembly. Blanket used slugs of depleted uranium bonded in stainless steel tubes. The reactor was designed to be controlled by only 2 control rods. However, provisions for 8 others as safety rods were built into the design of the unit.
Wow, controlling something with just 2 control rods. Number I'm used to hearing is around 50. It does depend a lot on your design type, but it's really just showing how small this reactor is.
At the time of the meltdown, only 7 had been installed. However, the reactor had been successfully operated with as few as 6 safety rods.
So when he says safety rods, the control rods in a reactor are enough to shut down the reactor by itself. The safety rods are so you can have additional shutdown margin over what is minimally required to shut it down. In fact, the shutdown margin calculation is even more conservative because it assumes the control rod of the highest reactivity worth, the rod that just happens to be in the position for this core cycle that it absorbs the most neutrons, stays fully out for whatever reason. But the reason why you have so many safety shutdown rods is so if the control rods fail to shut down the reactor, the safety rods will do it. And during a reactor trip, an emergency shutdown, and they all insert, it's going to shut down the reactor really, really fast in a matter of a couple of seconds.
During normal operations, the safety rods were held out of the reactor core, ready to be used in the event of a scram. Out of the two main controls,
Scram is another word for reactor trip.
only one was used for major regulating of the reactor's power, with the other being used for shimming, i.e. fine-tuning. All the rods were of a poison-type design employing enriched boron-10. Right, this leads us up to October 1966. In the 9 months prior, a total of approximately 717 megawatts of reactor operation was logged. These operations included a 60-hour test at 100 megawatts. During this extended test, some temperature abnormalities were recorded, however these were within design spec. A test was planned for the 4th and 5th of October. It was intended to measure temperatures at the reactor vessel transfer rotor in the number 1 steam generator and the sub-assembly sodium outlets, check new pressure control adjustment on the main steam bypass line, and adjust the automatic feed water flow control system. On the 4th of October, the reactor was gradually started up to 1 megawatts to heat up the coolant to just under 518 degrees Fahrenheit. A fault in one of the steam generation valves delayed the upping of the reactor output to 1:45 p.m. on the 5th. At 2 p.m, the reactor was operating at 5 megawatts. An issue with a boiler feed water pump meant that the reactor power was reduced to 2 megawatts for 20 minutes. Once the issue was sorted, the power rose to 8 megawatts.
So when starting up a reactor and raising its power, a lot of it is you're waiting on the secondary plant to start up its systems. For instance, at the plant I worked at, you had the startup feed water pump, and feed water is the water that feeds the steam generator up until about 20% reactor power, and then you started feeding with other steam generator feed pumps at around 30%, 60%, and then by the time you get up, and then before you get to 100%, you'll have turned off the startup feed pump and you're running with the main steam generator feed pumps. And that's just one secondary system. A lot of it involves just gradually starting up more and more systems in the secondary plant as reactor power goes up, because some of them require reactor power to be at a certain level before even turning them on.
The reactor was then put on automatic control until about 3 p.m, reaching a power of 20 megawatts. The reactor operators observed variations in the automatic control system.
Automatic control, this is early in history for relying a lot on automatic control. So at least at the plant that I worked at, you still manually withdraw control rods during a power ascension. Now the turbine is moved into automatic control, but you typically have it gradually raise speed at a certain ramp rate and then stop, or not raise speed, raise load, electrical load, raise load in terms of megawatts. I don't know about automatically raising power. I've never done that.
This problem had been experienced in the past at about the same power level and was thought to be interference picked up by the control system. The operators placed the reactor under manual control. As had happened before, the interference ceased and the reactor was put back onto automatic control for the power rise to continue. Just after 3 p.m, a staff member in charge of the operation saw that the control rods appeared to be withdrawn further than normal for this power level. Both the shim and regulating rods were approximately 9 inches withdrawn. Usually at this time the rods would be at around 6 inches.
And that's the other reason. So the reactor operator is kind of given a list and a map, a spreadsheet of approximately how far the rods need to be withdrawn, or what the turbine load is, what the steam demand is, and other control parameters they can use for reactor power at a certain level. Usually it's given in terms of percent, but it could also be given in terms of thermal power and megawatts. It's all the same stuff, really. But that is another reason why typically did it manually.
Normally high sodium outlet temperatures were being indicated over 2 sub-assemblies. At this time the power output was at 31 megawatts. At 3:09 p.m, radiation alarms in the upper reactor building ventilation system duct alerted the operators.
Ooh, that means you got a leak, is what that means.
Elevated radiation was recorded in the following areas: the 6-inch exhaust line from the upper reactor building, the 3-inch exhaust line from the machinery dome, upper reactor building and machinery dome exhaust, the waste gas building valve room, and the fission product detector building.
So high radiation in the reactor containment So yes, high radiation in the reactor containment building is one of the first indicators reactor operators are trained on, that, hey, there's a leak somewhere, because after all, it should be well contained within the reactor vessel, within the reactor coolant system.
The power of the reactor was quickly reduced to 3.3 megawatts as operators scrammed the unit. The containment building was automatically isolated, although there was no one inside.
Reduced to 3... Wait a minute, so reactor power should go all the way down. Is he talking about there's 3.3 megawatts of decay heat left?
At the time, a Class 1 radiation emergency was announced. This is the lowest in severity, and management took the decision that no additional measures were required. The FC was notified immediately.
So, emergency planning was... This is well before my time as far as emergency planning calls have done, but typically you would have, if there is a reactor leak above a certain threshold, usually a pretty small threshold, for greater than 15 minutes, is what's known as an unusual event, which is the first classification. So that would be classified as a class 1. And at the plant I worked at, that was like a really small number, like less than 30 gallons per minute. And to give you a sense of scale, now granted, I worked at a pressurized water reactor, so things are going to be a bit different for a sodium-cooled fast reactor, but the level 2 emergency or an alert is at 200 gallons per minute, and that's when you'd emergency shut down the reactor and initiate safety injection to ensure the core is safely cooled and covered with additional sources of borated water. Water with isotopes of boron-10 in it in the form of boric acid to ensure the reactor remains even more shut down than with all of its control rods and shutdown safety rods in there all at the same time. And 200 gallons per minute is about a 1/4 inch leak in a reactor coolant pipe. That's how much pressure is in that reactor vessel, is in that reactor coolant system.
The reactivity levels and the detection of fission product contamination in the cover gas indicated that fuel melting had occurred. Since a significant amount of fuel melting could change the pressure characteristics of the core.
Now this would take more time to make that assess of how much fuel damage has occurred. That can take hours to days. The emergency shutdown and making the decision you have a leak to that, we're talking in a matter of minutes, typically less than 5 minutes.
Tests were conducted to determine whether several subassemblies were substantially blocked or damaged. For the next year, the reactor was inspected and many fuel elements were...
Yeah, it's going to take a lot of inspections to figure out, to assess something like this, basically how broke your reactor is.
...moved for analysis. Investigations showed that 2 fuel elements had melted together and a third had bent but had little internal damage. In total, 3% of the reactor's fuel had melted.
So this was a similar type of accident with fuel damage, but it being fully contained to the 3 Mile Island event. Both events broke their core, though this event broke their core less. But this one isn't as remembered as the 3 Mile Island. Now, could be differences in American culture between the 60s and 1979. Could be the fact that the China Syndrome came out couple weeks before 3 Mile Island, for instance. But this is a very similar type of accident. Granted, it was less severe, but the impact on the public was about the same.
Damaged assemblies needed a lot of force to be removed from the core, necessitating parts of the reactor to be dismantled. On top of that, the 2 bonded elements had to be cut apart for removal. During the inspection of the reactor, a foreign object was found blocking parts of the lower plenum, starving coolant to some of the fuel elements.
That right there is the origin of the FME program, or the Foreign Material Exclusion program within the nuclear industry. And I say the origin, mainly this is why it is so robust. Technically, it exists in other industries, and it exists before. After all, foreign objects getting lodged in sensitive equipment, causing millions of dollars of damage. This is nothing new back in the 1960s even. But the fact that it caused a nuclear accident is why this program is taken so seriously. Now, for those of you who have watched my previous videos, you know I've talked about the FME program before, usually in the context of spent fuel pools and not wanting things to fall into the bottom and potentially messing with nuclear fuel. But it applies everywhere within the nuclear plant, especially things that can affect the reactor core, but even in non-nuclear parts of the plant, such as the turbine building. every job has to have an FME assessment done by FME qualified individuals. Not everyone on site is FME qualified, so plans need to be done and peer reviewed. You need to have an FME peer on your team and an entire FME section of your pre-job brief. There are FME barriers and zones in place, and a lot of them are around really sensitive areas, such as the open cavity above the spent fuel pool, for instance. And within these FME zones, there are FME monitors that log all of the equipment you take in with you. And there's a lot of equipment that's prohibited, such as tie wraps, for instance. They're not allowed anywhere near these FME barriers. And the FME buffer zones are the buffer zones that you can't even bring in those restricted pieces of equipment. When going anywhere near these zones, all workers need to be FME ready to have all the appropriate devices and security measures in place before going anywhere near these FME zones. Could be as simple as lanyards or fail-safe security things so your safety glasses don't fall above the spent fuel pool, for instance. Certain jobs have sign-offs that they need an FME device installed. FME devices such as this 9-inch pipe cover. Don't want any open holes that could possibly lead to the nuclear reactor. Some jobs even have FME 2-man closeout inspections required. And yes, the forms I saw at work actually said FME 2-man, which I gotta say is a bit sexist. After all, there's really no gender bias between the usage and inspection of FME devices. And there's a lot more to the FME program. It's actually continuously evaluated by industry consultants and self-assessments, so every power plant can continue to get better at their FME performance. This is one of the main driving forces, this particular accident.
This was discovered by draining considerable amount of coolant and the insertion of a borescope. The obstruction was part of 6 zirconium alloy panels used to direct coolant upwards to the reactor. It was suspected that dynamic flow forces caused sufficient flutter in 2 of the zirconium segments to break loose from their zirconium machine screws. However, this did not occur until a relatively long period of operation of the system. The objects were recovered in March 1968.
And that's why a lot of these closeout inspections typically look at things and not just how they're doing now, but how they behave over several years of operation. Because ideally, nuclear power plants, typically in the US, get a license to operate for 40 years, and a lot of them are extending their licenses for an additional 20 and possibly another 20 after that. So you want your equipment to run for the long haul. So that's why these inspections need to be done very, very carefully.
The repair works to the core used a specially designed remote control tool capable of withstanding the radiation within the reactor. The safety confinement of the primary coolant loop contained an estimated 10,000 curies of radiation. However, this presented a problem in repairing the reactor.
So a curie is a measure of just raw radioactivity, not dose specifically. That depends on what it is. But a curie is a pretty big unit. 1 curie is 37 billion disintegrations per is 37 billion atoms being disintegrated per second. So you're looking at something on a macroscopic scale here for sure.
Although 3 elements were damaged, the remainder of the assemblies was still salvageable. The reactor was pressed back into service in 1970 after the repair works. However, by this time, funds had been depleted for the project, and the aging equipment meant that Fermi 1 was shut down for good in 1972. The accident of Fermi 1 was used as an example of the dangers of nuclear reactors.
That's the other thing. When you have fuel damage, even a relatively small part of the core, just the additional remediation costs can easily make it that reactor will never operate again, or sufficiently shorten its lifespan.
Publications like We Almost Lost Detroit, a 1975 Reader's Digest book by John G. Fuller.
So, did we almost lose Detroit? No. This accident was safely contained. It wasn't luck or anything that prevented it from getting worse. All the radioisotopes were safely contained within the reactor containment building. Not to say this reactor was completely safe, because it obviously wasn't. There's still safety issues associated with using a liquid sodium coolant that probably have yet to be addressed, but that's an exaggeration.
A song with the same name was released by Jill Scott Heron and Brian Jackson in 1977. However, compared to many other atomic incidents, the meltdown at Fermi 1 seems pretty tame, as the confinement structure worked as it should, and no official reports of radiation release were reported.
So he uses the term confinement structure. He means the reactor containment building. technically the definition, he means the reactor containment building. These buildings are designed to handle not just keep radioactive material in there, but keep an explosion of radioactive material in there. Because they have pressurized vessels, while a liquid sodium reactor isn't pressurized like a pressurized water reactor. It's still well above atmospheric, and there's all kinds of hazardous material that need to be contained in there. Compare that to, say, Chernobyl, which really had nothing that met the true definition of a containment building in terms of being able to withstand explosion.
In comparison to the Waltz Mill accident in the last video, it seemed that they operated Reactor quickly enough to prevent a more serious accident. In 1975, it was officially classed as decommissioned by the AEC. However, after the formation...
So the Atomic Energy Commission, this is older because this happened back in the 60s, and a lot of the remediation in the 70s. But it's the Nuclear Regulatory Commission now. The Atomic Energy Commission actually used to do the job of both the Nuclear Regulatory Commission as well as be the commission that promotes the use of nuclear energy. But now that the part that promotes it is now under Department of Energy, the Nuclear Energy Section.
NRC, the definition of the unit was reclassified to a safe store, necessitating more decommissioning works.
There you go, and here we show the Nuclear Regulatory Commission logo.
In 1996, the works for decommissioning continued. However, the work again stalled in 2011, with the site keeping the safe store classification. The site currently has a possession-only license due to expire in 2025. It is planned that decommissioning will be continued for the purpose of removing the remaining residual radioactive material and terminating the Fermi 1 license.
That's another really nasty thing about nuclear accidents is decommissioning is a pain, and you're going to far exceed however much money that reactor made for a very, very short period of time. So that's why it is such an aggressive, even accidents that don't even hurt anyone, the financial risk is immense, which is why so many safety systems are so heavily invested in, and as well as just robust programs like a strong FME program.
Fermi 2 is still in operation to this day, providing electricity to the local area. The Fermi 2 operating license expires in 2045. The Fermi 2 operating license expires in 2045.
Yes, Fermi 2 has had a license extension, which is why it's going that long, because it was not built in 2000. It was not built in 2005. Nothing was. Thanks again for the recommendations for this for Plainly Difficult's channel. That was all in all, I thought that was a pretty good overview, and it's just interesting why this accident didn't have the same amount of fear, because it was a similar type of event as 3 Mile Island, but I digress. Thank you very much for watching. I'll see you next time.